So, hello, good morning, everybody. It's here in Peter. I was wondering who was the person who was talking about. So, for me today, I would like to first thank the organizer of the conference for giving me this opportunity to share with all of you this research and my experience in this special play that is street art. I wonder how I came to that place. Really, 3-4 years ago, was a colleague in physics working in chemoembryonics. In other words, in chemical garden. We were trying to find a joint topic for a research project, and he suggested me to start here. Oh, when do you, well, why not do we apply for a project in street art? Because it's a big chemical garden, a big natural chemical garden, but also he said that there are clay, it's made of clay. So I was quite curious to see saw the images and how this can be just a clay deposit. So I decided to apply. We were very lucky, and the Andalusian regional government gave money or granted for the project. So after that, we started this, for us, I think, this fantastic scientific journey. Okay. So first, I would like to introduce some concepts about the hydrothermal, the marine hydrothermal system. Probably many of you know about that, but usually in this clay conference, we have two general background, no? The chemist and the geologist. So let me give some concept to remind that. So the hydrothermal vent, the submarine, I'm going to talk always of submarine hydrothermal vent, were discoveries in the Galapagos Reef at the end of the 70s during a campaign of the Woodhull Oceanographic Institution. They observed temperature anomalies, and then finally in the 1979 they discovered the black smoker, where some chimneys with huge plumes of dark color, high temperature, means 300, 400 degrees, at very acidic pH, between 3 and 5, and all these plumes were minerals that include sulfides, magnesium, manganese, and iron oxide, and then other kind of mineral like anhydrite, barite, etc. There were also the volatiles, mainly hydrogen sulfide, CO2, and all these were more or less associated to, say, the volcanic context in the spreading centers. And the characteristic feature was the chimneys and the plume. But in 2000, there was another milestone in this research. That was the discovery of the lost city. The lost cities is completely different. It's also the name of a field. So when you look in internet, you go to the field instead to the hydrothermal vent. The strange thing, or the different thing compared with the smoker, was that lost city was of axis, was in the intersection of the Mid-Atlantic ridge and the Atlantis fault zone. Well, in this area, and the structure would observe over all oceanic crust. What was also different, and the effect was not the heat fluid coming from the seawater warmed by the volcanic system in the spreading center, but in this case was serpentinization reaction. Serpentinization is exothermic reaction, and also seawater that interact with the mantle rock and became hot. And this produced also an hydrothermal system. Here is the sketch of the outcrop. And that's the characteristic. You see, this is the images of the towers on huge pinnacles, almost, they arise 60 meter high at a depth of 700 or 800 meters. But the environment was completely different. So the water, the solution was cold, 40, 75 degrees. And the pH was not acidic, but alkaline, 8, 9, 10 in pH. There were also volatiles, but the main volatile in this case was hydrogen and methane. And the images was spectacular in the sense there is no plumes, but fantastic white towers formed of aragonite and brucite, and calcite coming from the aragonite. The researcher involved in this research finally get to two ideas. And the first is what a much larger proportion of the oceanic crust may be affected by hydrothermal activity and also microbial life than previous thought, because all the research was concentrated, was focused in the spreading center. But now could be quite wide. And then, because all the hydrothermal systems have a unique form of life, that alkaline hydrothermal vent could be one of the environment where the life could emerge. And this have attracted a lot of research. In this map, you can see the hydrothermal vent known, and also that was our inferred. And you see they are aligned along the see, in the first figure is the fire ring, for example. In all of them, we have steep gradients. Steep gradient temperature, pH, redox, concentration. That means energy. And it will life need, energy. So here is the great interest for the environment for the emergence of primitive life. But we are talking about a slightly different kind of hydrothermal vent. It's the shallow sea hydrothermal vent. Here you have this is the boiling water curve. And these are the dots correspond to conditions or temperature and depth for the vent we have seen previously. At 200 degrees, there is an inflection point in this curve. What means? That means that above 200 meters, the boiling water curve depends more from temperature than from pressure. And below 200 meters is pressure, who mainly control the condition. So in this area, below 200 or above 200 meters, we can find the shallow sea hydrothermal vent. And there are also another important point, is this depth is almost the maximum extension of the photic zone. So compared with the deep hydrothermal system here, we can they can coexist photosynthetic and chemosynthetic microorganisms. And the concept in this case is not necessarily linked to the divergence plate areas, but also other volcanic areas are also place where fluids is the discharge of hot fluid. You have there is the map with more than 70 spots over the world. And here is Stritan, that is the object of, and this is Stritan. So it's a very, very nice place, but Stritan is, this is the the Eja Fjord in North Iceland, and Streatham is on the sea level. Yes, I had the opportunity to visit that. Not inside, I'm not a diver. This is also, is Iceland. Iceland is in the apex of a hotspot, and it's a unique place where the American and Eurasian plates spread, and this spreading is go to the to outside to the surface. There is an intense volcanic activity, and around the volcanic activity, we have high temperature hydrothermal system, but north and south we have a low temperature hydrothermal system. This is the fjord. The fjord is north of Akureyri, which is the second largest city in Iceland, and it's all this yellow spot are prospection and exploitation of hydrothermal water for heating and energy. The hydrothermal system is around Hasteri in the fjord. The bedrock in the area, because Iceland is geologically a very young country, are basaltic lavas with deepest loading to the south-southeast. And this is associated to the Thorns fracture, and there are a system of north-northeast and northwest trending faults. All this feature is important for the emergency of the emergence of the fluid. We have here is the data about the fluid, and between brackets is the seawater. To compare the gradient, we have gradient in temperature. Temperature is about 70 degrees, about 10 in pH compared with 8. And the hydrothermal fluids are enriched in silica. It's almost saturated in silica. The seawater, on the contrary, is very rich in sodium, magnesium, and calcium. There are a very small amount of aluminium that came with the hydrothermal fluid, because there is almost nothing of aluminium, no aluminium in the seawater. The isotopes analysis indicate that the fluids were not seawater, was continental meteoric water. It's meteoric rain falling in the high inlands to the south of the fjord that percolate deep in the bedrock, that interact with and dissolve the minerals in the bedrock, and after several kilometers ascend to the surface through these tectonic features. And in this path, the fluid becomes hot, and this is the origin of our hydrothermal system. Here is the fjord. I said it was Hasteri, and really there are two, in this field there are two areas. The first is Anarnes-Streatham. Anarnes-Streatham is the seafloor in this slope, inside this 20-30 meters depth. Anarnes-Streatham is alignment with almost with northeast or north-northeast trending of different chimneys for 500 meters. These chimneys are not active actually, or at present. The other field is Streatham. Streatham is that I don't have this a big a whole representation. It's a 65 meters in depth, and it's formed by 3 columns. These 3 columns is the biggest Streatham. This is the only active, which is 45 meters, and the other is 25 and 23 meter high. This reached a level of a depth of 20 meters, and all the sample is done here because it's a natural reserve, so it's protected, and so the people interested in the sample must be from this area. Oh, let's see. Okay, these are pictures from Erlendu Bogason. Is the the owner of the diving center and the person in charge of the protection of the area. So you have Streeton here, the big one. This is the appearance. So you have, when people see, people who dive can see, it's a dark tower, a tower completely covered of different line four and microorganisms. And in some point, there are white pinnacles like this. This is the apex of the chimney, where water is not bubbling. This is leaving the tower. So the tower is a big channel where the hydrothermal fluid go ascend and go to outside. Let's see how this works, because yeah, you have some videos obtained during the sampling campaign, and see there is a lot of life. So you see the water is 7 degrees more or less, the average, but here the temperature may reach 20, 25. So it's a comfort place for many fauna in the area. Okay. So since the discovery of Streeton at the end of the 90s, during geothermal prospection, it have attracted the interest of some scientists, some groups. Probably because it's underwater, and so is also Iceland is in the middle of everything or in the middle of nothing. Really, it's too much interest considering the number of groups working there. And people, or the scientists, our colleagues, do the interest in the geochemistry, the mineralogy, the structure, the tower, and especially in the last time about the microbial, the ecological of this microbial community. There are some aspects that is not, for me, it's controversial because it's biogenic clays. But looking at the sample, look at that, we saw there were some contradictions that we found when we studied the sample. So we collect, considering this, we fixed three main objectives, three main questions. So what are chimneys made of? It's really a saponite or something else. What is the internal structure of the pinnacles, the towers, and how the chimneys are formed? I left another question. Why in this point and not in another one? So we organized the sampling campaign the last summer, obtaining a sample of, we call fresh or active hydrothermally active sample. So it was the white sample, because we want to know how they precipitate. And then we also obtain a small fragment of the chimney, is that one, with its like half meter tall. The batch of analysis to characterize that, you may imagine, I showed that, optical microscope, mineralogy analysis, as well as all the microscopy techniques. The appearance of the sample is quite different from what I call the active area with the column. On the column, the inactive or less active period. The active areas are whitish, brittle, and very porous material. So it's a very low specific weight. In this sample, there is no apparently presence of living organism, maybe bacteria, maybe, but there is no other plant or animal colonizing the surface. There is channel parallel, also parallel to the vertical direction, and this channel are the space between bundle of oriented fiber and filaments. And with age, this white color becomes cream color. On the contrary, the chimneys are brownish, is less porous, but have big channels compared with the active area, have a occluded channel, have remains of algae, shell, and etc., and also its sediments trapped within the material. Concentrating here, these are some pictures showing with some microscope is the filaments, wavy filaments. Then in the surface of in the walls, sometimes it's micro chimneys, similar to the big tower by some millimeters that have this aspect in section, and then also channels start to fill with mesh structure. All that resemble the chemical garden. A chemical garden is a structure with the aspect of the vegetal aspect, but made purely with the addition of chemicals in particular solution, but it's purely inorganic structure. To understand how was formed, to understand the structure, we decided to perform tomography of the samples. And this is a cross in the figure they will to show is the cross section, and this is a parallel section. And these are the reconstruction tomographic, 3D reconstruction. In the first, you have is really you see here it's an open space because the black is porosity, and you may see here. I thought you were seeing the mouse on the screen. So all these spots are, you see these filaments. So it's the filament here, and then the channel they lead in the side. Porosity is almost 75%, and it's completely open porosity. So all the porosity is interconnected. Let me show this Rico's video. Let's see. Okay. So you may see the filaments. So we are moving up, but the effect is similar to the growing of the filament when the hot fluid is ascending within the column in contact with the water. So it's a result of a Boolean effect that produced the growing of the towers, the filament. This is the extreme, is the column, so it's a non-active area, and what we have is that. This area is the filament, but the filament are close packed because they start to grow, join, forming the bundle, closing the porosity. But we have other material. This is the sediments filling the big holes because we have deduced is that the porosity is something dynamic. So the filament grow, open they move really, and part dissolve, leave big channel where for the circulation of the fluid. And in addition to the filling of the sediment, we have some remains of shell, like here is in some part. I also have the video. Oh no, yes. You see, it's different, completely different. And we thought this non-active area is what is giving the scaffolding for the tower. Because in the other, this white porous sample cannot be supporting, no? A 60 or 45 meter structure. See, all these are mainly filaments. These cracks are probably for drying the sample outside the sea. Mineralogy. The first and the fastest was the FTIR. And apparently, yeah, many of us will say this is a clay. We have the trioctahedral clay with magnesium, the OH stretching associated to aluminum and magnesium, but this very, very low intensity peak. Then these are the corresponding bending vibrations. The strong, intense band associated to silicon. We also have in some sample band vibration of carbonates, and there are a lot of water. Even though the samples were heated for overnight, 200 degrees, there are a lot of water. These are, we deduced that in fact there is as we call saponites and magnesium clay, but also there are a silicate or a material that is not really a clay. The diffraction helped, yes, partially help us. We tried, usually we work in reflection geometry, but with the reflection geometry was impossible. We only obtained some background, yes, it was like a hill, no, a small hill. So we went to transmission, and in transmission, in transmission, we obtained these patterns. The upper, these are a little bit magnified because otherwise we may see the band. It's an intense background. This band indicates we have amorphous material, a silicate or a silica-based amorphous material, in addition to the clay. The clay is we say it's a saponite clay, or even it could be a serpentine-like, because the 060 band is 1.54, 1.53, and sometimes we may think that there are two different reflections, but we are not sure. Basal refraction, in most cases, are absent. Yes, we have in some of them a small one, but it's not 14. It moved even to 18 angstrom. In the oriented mouth, we don't get anything. We also, the sample is quite heterogeneous. This is the sample 3, with it is 1. In different materials gave, you see, these different compositions. You have here we have almost exclusively the saponite, and here we have aragonite in different quantity. In the column, we also have areas where only have smectite, the saponite, but in other places there are the sediment, the mineral from the sediment, like these plagioclase. There are also cristobalite, calcite, etc. So it doesn't help too much. We went to the microscope, the electron microscope. Here I have scanning images. This is a bundle of fibers. The fibers join in this area. This is the growing direction, so it's the flowing direction. The surface is, you have all these protuberance, and really we are, Antonio, at the limit of the resolution of this microscope. The inside is quite homogeneous, so we don't see any structure separating the different fibers of the protuberance. But there are another fibers that are much more beautiful than this one. This is, we have a honeycomb structure coating the fibers. And we assume that this is the clay. These plates, curved plate, or the saponite. This is a fracture fiber and give us in some way the structure. So the layers, these clay layers, are limited to the outer part, being the inside similar to that one. Compare the scale is 1 and this is 1, so it's a big bundle of fibers. And then it's important, there is no hole inside. Yeah, are filament, not tubes. Okay. But in addition to the filaments, we have another of the characteristic feature is the spheres. In some areas, on sample, there are a lot of spheres, quite homogeneous inside, about 2 microns. The spheres also coalesce one to others. There is no difference, separation between one of them. Some are also coated by plates. You see here detail of the plate. This is 200 nanometers, so it's maybe 10 nanometer, 20 nanometer, just the thickness of this curved folded layers. And this sphere we observe in cavities, so it's in some cases lining cavities. So this we deduce that it would precipitate in confined environment in areas where the fluid flow was reduced. So I remember I told about the dynamic of the porosity. The composition is magnesium silicate with always a small amount of aluminum, and the composition is quite homogeneous, irrespective of the area of the kind of particle that we are analyzing. It's changing the intensity of the relative intensity of the different element, the signal, but that's all. Here is no bromide, it's aluminum. So with this, what we can obtain with scanning. In transmission, we prepare the sample in 2 ways. We want to go deeper in the scale. So we prepare sample on copper grid, so it's some different areas ground, intensively ground, and deposit on the grid. But also we prepare the sample in resin, and we prepare the ultra thin sections. And what we could observe was equidimensional irregular fragments of material. We also observed the fragment of the fibers that I showed previously, and also aggregate of flakes. And this is, I show one of the best examples, because the most common is like this. So I think it's very, the low crystallinity, very small. This is a good one. So the spacing, the common spacing is between 10 angstrom and 14, 15 angstrom. You see this, the lateral continuity is very, very limited. And also the stacking. So we have the stacking 2, 3. In the best case, we have 5. We may say, oh, but this is a thicker packets. Yeah, but it's different packets of coherent domain. And here, this is apparently there is area where we have only 1 layer. And this is the case. I showed this one. We measured a 7 angstrom layer, but this is very occasional. So the common is that one. And this is where the isolated clay fragment, but the most common was the fiber. This is a nice picture. It's a section, a fragment of a fiber. And yeah, we have a very dark core with this, a good light. So it's like a crown. You see the feather of something native used. So it's this crown. And the electron diffraction of the core, you see. So it's amorphous. If you can identify anything, please tell me. So it's amorphous, it's not familiar. But the flakes have, in some of them we get the electron diffraction pattern, and the electron diffraction pattern is compatible with saponitic clays. In scanning TAM, you obtain the picture and analysis in the flakes and the core. Analysis, then we recalculate then as a structural formula, and for the layers, this part is close to saponite. We always have, everybody that have worked with the structural formula knows that everything there is at least one element when we don't know where is exactly located. Here the problem is magnesium, as always, because we didn't want to change the exchangeable cation with another one. We prefer to use the sample in the natural state. But here in the core, the analysis, it doesn't close because we have, in this case, an excess of magnesium. So in the core, in this fiber, the core is enriched in magnesium and need to compare with the saponite clay. This is an ultra-thin section. So it's similar to the previous picture, but now we have here the structure. You see the amorphous core is a reticular area. Yeah, it's amorphous, so this electron diffraction is from this fiber. So we don't see anything, or the crystallinity is extremely low. What can you measure in here in terms of high resolution? Almost anything. Then evolve to intermediate band with this here. You see here the different aspect. It's a cross-link area. We couldn't identify any lattice ring in this area, but it's the place where the plates grow. It really resembles some plants growing from the soil, no? And the smectite layers in this crystal, we made a FFT image. We have two points to group, 4.5, and also, yeah, the spacing is 15. So it's the outside of this is a clay, and this is a sphere. This is an artifact of the diamond knife, so this part, but the core is very small, very reduced, because the size is, we compare, no, the filament and the sphere, but the structure is always the same, the cross-link area and the clay layers. We analyze with a microscope about 100 spots, no, in different samples. I plotted here in this ternary plot, having the silica, the dioctahedral, and the trioctahedral and the dioctahedral component. Most of the analysis corresponds to amorphous and crystalline material. But the crystalline, the layer, like here, in this area, which is in where the saponite still inside, have the composition. Some of the layers have a little bit enriched in magnesium. We may thought that this intercalation of serpentine layers, or maybe also magnesium hydroxide within the layer. We don't know. We cannot be sure because, you know, it's extremely low, the crystallinity. But the samples are in general enriched in magnesium or enriched in aluminum. And this is particularly interesting because the green square corresponds to this sample. It is what we call a white crust. The white crust corresponds to the sphere. So we said that the sphere were precipitated in confined environment. Yeah, and this could confirm this hypothesis because the fluid circulation is restricted, is not the average, and could be responsible of this dispersion. The average clay structural formula is that. It's mainly a saponite, but I prefer to say it's a saponite stevensite because we don't know if there are vacant in the octahedral structure. And here you have the range of variation of the different cations. Well, I said that Streetan works as a huge chemical garden. I say that the chemical garden is a set of, something changed the text. A complex biological looking structure created by inorganic, mixing organic chemicals. And chemical garden is said that it's an example of cell organizing non-equilibrium process that create complex structure, always within in biology. But there is also the inorganic world that produce beautiful and complex structure. And in this case, this cell organizing structure have the capacity of self-propagation. And the clays under fluid advection. And they form these semi-permeable membranes. And this occur in area with a steep gradient. And the key is osmosis, it is the buoyancy. This is a chemical garden. The chemical garden and cell that's a game for chemist game for children. But these are beautiful pictures and correspond to biomorphs. So it's pure inorganic. So this is the sketch of the Streetan Tower, and the sketch it's a big chemical garden. So it's the hot fluid with emerge from the bottom and in contact with the seawater start to go up, to flow up, because it's 32. This is 7. But then the temperature modified the density. This is the density of the seawater, this temperature, 1.027. But for the hydrothermal fluid, is 0.977. So it's a buoyancy effect. And in the path going up, is interact with the seawater, producing the precipitation of the silicates. There is a mixture. I'm not sure if there is mixture of its transfer from magnesium because it's necessary for the precipitation of the tower. The aluminium is supplied by hydrothermal fluid, but the result is all this structure where the fluid continues to go up, and it's like this big membrane. But this big membrane is made partially of clay. Well, it's not so young. The tower had 11,000 years. It's 11,000 years old. But here we discover is clay, but really is not clay. The tower is formed by amorphous silicate. We don't know really how they really form, but we thought it's not biogenic. In our evidence say it's purely inorganic, and the presence of clay is limited, quite limited to the external part. So the first is the precipitation of the filament. This filament that grow and then coalesce and modify the structure, and then the fluid flowing in contact with the filament produce this additional cation chain lixiviation that made the rearrangement of the amorphous silicate into this area. And finally, porosity is modified, and finally, when all the structure is there, it came colonizing the living organism. But the living organism go there because they feel comfortable with the temperature and also have a structure to go closer to the surface. Thinking that we are in the north, so the light is more, there is not so much light like here in the Mediterranean. So it is fantastic place for growing and for saying the microorganism. But I think that I have answered to my 3 questions. I said partially, because I think there are, for me, is more question opens. But in any case, this could be the inorganic cell that said the theory of Mike Russell about the hydrothermal, the alkaline hydrothermal being the events could have harbored the origin of the emergence of life. But the emergence of life, because prebiotic chemistry, abiotic chemistry could happen confined in these cells. And that's okay. Finally, just to thank all the people who have been in some way involved in this, for me, fantastic journey. My colleague in the project, Julian and Sander, my master student, Elizabeth, technician and also colleague. The role of the Erlendur Bogason Street and Center was unique. It made possible the project. And then Iñaki, Saverio, Antonio, the Icelandic Geological Surveys gave information with Björn Gautoson, and then people discussing, and we keep some joint research at present, and then the group of the COS meeting in Iceland in last March. Financing, again, thanks to the government of Andalusia and also the Coast Action Group, founded the meeting. And that's all. Thank you very much.